Ну, хорошо, да.
Okay. Let's continue our lectures devoted to stochastic analysis. And let us recall what we did last time. We discussed special polynomials from standard Gaussian variable and introduced the following object. Suppose that psi is standard Gaussian variable. And we consider last time such random variables alpha z. Alpha is square integrate and measure with respect to psi. I denote this vector by the following notation. Alpha is from A2 and sigma field is generated by the random variable psi. We proved that one can introduce the following family of polynomials h n of x is equal to minus 1 in n power e x square over 2 multiply on the dx nth derivative of the function e minus x square. And we prove that every variable of such type, which is square integrate as measured with respect to psi, can be uniquely expanded into the series from n equals 0 to infinity, an, h, and psi. Corresponding summands are orthogonal, and moreover, we know that the quadratic norm of this Hermite polynomial from standard normal variable psi is equal to n factorial in 1/2. In order to understand how to find these coefficients, we introduced a very important and famous object, which is called stochastic exponent. Namely, we consider special random variable of such type. This random variable depends in our case on the number lambda and is defined as exponent of lambda psi minus lambda square. It can be easily checked that this random variable is square integrate. Moreover, it has a very nice expansion with respect to Hermite polynomials of psi. Namely, we have the following expression: E of lambda is equal to sum from n equal 0 to infinity lambda in n power over n factorial, and here is h n of psi. Due to this expression, orthogonality of summands in this series, and the fact which we mentioned that the quadratic norm of hn of psi is equal to n factorial in 1/2 power, we have the following interesting relation. That expectation of alpha lambda multiplied with e lambda is equal to sum from n equals 0 to infinity an lambda in n power. And it can be checked that this is analytic function with respect to lambda because of properties of an. This series must converge. And we mentioned last time that for this series we have that expectation of alpha square is equal to the sum of n factorial an squared. Since this sum is finite, it is easy to see that this function is analytic. And in all complex plane, lambda can be chosen complex also. Since then, it's easy to see that coefficients of expansion of random variable alpha with respect to Hermite polynomials can be obtained as derivatives of this function at the point 0. Due to this transformation is chosen to detect coefficients of expansion of alpha with respect to Hermite polynomials and has special name. Namely, we will say that this is Fourier-Wiener transform of the random variable alpha at the point lambda. Last time we write these names. So this is Fourier-Wiener transform of our random variable alpha. And before we proceed further, let me emphasize that the names, these two names, Fourier-Wiener, excuse me, in the name of this transformation are essential because maybe you understand that name of Wiener must be related here because we have Gaussian random variables and Wiener did a lot in investigation of his process and so on. But why Fourier? Why Fourier? Maybe you remember that one of the most important properties of Fourier transform is its very good reaction on the convolution. So we have the good property. If we have two functions and consider a convolution of these two functions, the Fourier transform of the convolution is equal to the product of the Fourier transforms of initial functions. This is the fundamental property. For example, from here, using difference approximation, one can get that Fourier transform of derivative is equal to multiplication of the free variable on the Fourier transform of the initial function, and so on. So the most important and most useful property of Fourier transform is its good reaction on the convolution. So maybe here we have to find something which also will have properties like convolution, and then we can apply Fourier-Wiener transform in order to get product. Yes, it is exactly this case. So let me introduce to you this operation. Firstly, let us guess what it can be. Suppose that we have two random variables which are square integrable. We have alpha and beta from our special space of square integrable random variables which are measured with respect to initial standard Gaussian random variable. Then, as agreed, we have the expansions relatively having polynomials for both of these variables. An, hn psi, and here is sum from L is 0 to infinity Bn hn psi. Then, as we have seen, we can produce its Fourier linear transform, and it will look like here we have alpha lambda is equal to the power series sum from n equals 0 to infinity an lambda n, also Fourier linear transform of beta at the point lambda is the same series from n equals 0 to infinity bn lambda. And as we mentioned already, these two series are converged on all plane. So let's consider multiplication. Let us see what is the product of these two series. It's trivial because we know the procedure, we know how to multiply power series. So the product tau alpha lambda and tau beta lambda is equal to the sum from n equals 0 to infinity. Here is the sum from k equals 0 to n. Here h k b n minus k multiply lambda in n power. Yes. So we have the following expression for the product of Fourier linear transform of our line. Here, one essential remark must be done. You remember that the coefficients there are not arbitrary coefficients of power series. They satisfy special condition. Namely, we know that that series of an square multiply n factorial is finite, bn square multiply n factorial is finite. Now we get new one series, and one can ask, maybe this series is a Fourier linear transform of some other random values. It is not true in general case, exactly because we don't know how that sum of n factorial multiply on the square behaves. But it can happen that it converges rapidly, and in this case, one can consider new random variables such that we denote it by alpha star beta, like convolution, which is exactly the sum of n equals 0 to 50, sum from k equals 0 to n, ak b n minus k, here is h n psi. So, as I said, it can happen that the series converge in square meter. It is not always, but it can happen. So we can consider such a result, and if this result is well defined, so if this series converge in square meter, then we will call this new random variable weak product. Weak product. This is a name of a random variable alpha and beta. From the definition, it can be seen easily that it does not depend on the order of alpha and beta here. Also, let us check some examples in order to understand how to organize weak product. Example. Consider a case when we multiply psi. Since both these two variables have very simple e-to-winner expansion, like this one, then it can be easily checked that this is exactly H2 of Xi. Moreover, by induction, it can be easily checked that psi n time is equal exactly Fermi polynomial. Also, from definition, it follows that operation of weak products is linear with respect to both multipliers. One can see that maybe weak product is organized as follows. We just substitute powers of psi by Fermi polynomials of the same order. It is true. And you see, and we will discuss today also, but you see from the previous lecture that Hermite polynomials are organized as follows. One can check that Hnx is equal to x in n power minus or plus something. Yeah. Here we have a smallest degrees of x. From this point of view, one can say this came from physics, that weak power is a renormalization of usual power. We subtract some terms of smaller powers. And we will see that this name is non-trivially related to weak operation. Moreover, you can find in the literature another notation which came from physics. You can find such one notation. Multiplication of alpha and b, and here is 2 points as a brackets. This another notation. Of weak product. And we will face situation which also came from physics, where the usual normal product does not exist, or does not well defined, or have a very bad properties, or cannot be investigated. Then people substitute it by weak product and continue to work with it, and sometimes get right result which are consistent with the experiments. So why it happens in such a good manner? It is due to the good properties of Hermite polynomials. Now let us came back slightly to properties of Hermite polynomials and try to find some special relationship between them. In order to find this good relationship, I will just use the definition. You remember that we define Hermite polynomial of degree n, like minus n minus 1 in n power, e x2 d dx in n power e minus x2 squared. So let us try to find next one. What is the expression for the hn plus 1 of x? One can see that it must be from this n plus 1 e x2 d dx n plus 1 and e minus x. But I want to have some recurrent formula. Due to this, I will use this one, the expression, in order to get the expression for this term. So from this line, one can check that d dx and e minus x squared over 2 is equal to minus 1 in n power multiplied by e minus x squared and multiplied by hn over x. Since then, I can substitute this expression in the right part for formula for hn plus 1. What I will get? Well, let us write it here. So I continue the calculation of this hn plus 1. I will get this expression minus 1 n plus 1 e x squared over 2. Then here there are n plus 1 terms. But I know what is n. So I just write here d dx from this expression minus 1 in n power e minus x squared over 2 hn x hn x. Let's continue. Let us continue. We have a good news. This minus 1 and n plus 1 and n give us just 1 minus. Here is x e x over 2. And here I need to take derivative of this expression. It's easy. So we have here hn prime x multiply this one minus x hn x multiply e minus x. Okay. Then let's do multiplication, which will cancel plus exponents and use this minus again, and we will finally get a very nice expression like formula. We will have expression x multiplied by hn x minus hn prime of x. Let us write this expression again, so we get the following representation. hn plus 1 of x is equal to x hn of x minus hn prime of x. To make this formula a real recurrent equation, we need to find this expression. What we need to find this one. Let's do this. Let us again use the definition. I recall you that we have the following expression. E lambda x minus lambda square over 2 is equal to the sum from n equals 0 to infinity lambda n factorial h. This was very useful formula which we got last time, and this is a power generated formula for Hermite polynomials. Now I want to understand what is h and prime. So what I can do, I can just differentiate both parts, yeah, with respect to x. So I apply d over dx to both parts of this formula. I can do this because of the series converge. This is a power series which converge with respect to lambda of all line, and with respect to x, it converges uniformly on the intervals, bounded intervals. So one can do differentiation, and I will get here lambda e lambda x minus lambda square. It's easy, yeah. It must be equal to sum over n equals 0 to infinity lambda n factorial h n prime of x. Yes, I just do differentiation in the right. But I have expression for this one without any derivatives. So I continue. I just have the following. In the right part, I will have this one. To infinity lambda n plus 1. Here is n factorial. Here is hn x. And it must be equal to this part. Sum from n equals 0 to infinity lambda n factorial h n prime. Now let us see on these sums as a power series with respect to lambda. They're equal for all lambda if and only if the coefficients under the same degrees of lambda are equal. From this point, one can have that we have the following relation. Hn prime of x is equal to hn minus 1. Here is nice formula which gives us representation for the derivatives of Hermite polynomials, and it is very nice kind of this formula, because you see the differentiation can be done exactly in the same kind as for powers. You remember, of course, the xn prime is equal to n xn minus 1. So we have exactly the same rule for differentiation of Hermite polynomials. Now let's back to the recurrent formula for Hermite polynomials. Now we can continue. You remember that we get the following: hn plus 1 of x is equal to x hn of x minus hn prime of x. This formula also is useful when we use it, but now we can finalize this formula substituting this expression to this part. What we'll get? We will get the following: hn plus 1 x must be equal to x hn x and minus n hn minus 1 of x. So we see here the recurrent expression for Hermite polynomials, and here the following remark must be made. Let me recall you that Hermite polynomials are orthogonal polynomials with the first coefficient 1. You remember we have here degree n and xn here with the first coefficient 1, and they are orthogonal with respect to standard Hauser distribution on the real line. There exists so-called Darboux theorem, which says us that for arbitrary finite measure on the real line, its result of the orthogonalization of the powers, so orthogonal polynomials with respect to this measure, must satisfy relation like this. But here there are some coefficients, A and B. And maybe NBN. And sometimes such matrix which arise here, you see that if you want to define the polynomial degree plus one, you must have the sum of polynomials, this one, so on, but only these two. So if you organize a matrix, you will have only such such table, and sometimes it's called Jacobi matrix, and also is well studied in mathematical part of quantum physics. We will back to this fact in the future.
May I ask you, so this for the general case by the Darboux theorem, there should be A_n and B_n without some, so x, so no dependence on x?
X must be. Surely x must be, because we have
so additional multiplication with some constants.
Yes,
and,
exactly.
And n also stays on the in the last summand.
Yes, and you see, it's not very hard to understand how to get this. Imagine that you have just some orthogonal system with respect to some measure. Yes, then how to get next one? You just multiply the previous one on x, and then try to manage what you have to subtract in order to get orthogonal. But you know that this guy is already orthogonal to any polynomial of degree at most n minus 1. So this product is already orthogonal to any polynomial of degree n minus 2. So we have only such sum. Yeah. This is just explanation of those things. But it is interesting fact that and use that for arbitrary probability measure we have such kind of relationship. In Gaussian it's nice, and this is purely property, and we will now to start to exploit exactly this property. How I will try to do this? Now let's came to the new subject of our lectures. After we have the expansion with respect to Hermite polynomials, we define big product. We knew the recurrent properties, formulas for Hermite polynomials. Now let us try to use its differentiability properties, and we now introduce stochastic derivative. Stochastic derivative of random variable. Let me recall you that if we have alpha which belongs to L2 and is measured with respect to our standard Gaussian random variable, then alpha can be uniquely expanded into the series An Hn of psi, and we have the following expression that the expectation of alpha square is equal to the sum from n equals 0 to infinity an and n factorial. This are known factor already for us, but now what I'm going to do? You see, we already know that Hn has a good expression for its derivative. So one can try to consider the following. One can try to consider the following definition. If the series if sum n equal 0 to infinity, then an hn minus 1 of psi converges in square mean then alpha is called stochastically differentiate let me for a moment. And stochastic derivative of alpha, d alpha, is by definition equal to this. Yeah. So we have the following definition, which is natural from the point of view that this is exactly derivative of the summand here, with respect to probability variables. Let me make this similarity much more deeper. So let me recall you that if alpha belongs to this family L2 sigma psi, then by the well-known theorem from the course of probability, alpha can be represented as f of psi, where f is a Borel function acting on so now let us find the relationship between existence of d alpha, stochastic derivative of alpha, and how it is related to some properties of f. Of course, it will be good to have some derivative of f, at least in some sense. And we will see that this is true. Let's start. First, let's start with the finite sums of our series representation. So take alpha like a polynomial sum p of psi. As we mentioned already, there are different branches of mathematics with the same notations for very different objects. It is common to denote polynomial algebra by the capital P. It is common for us to denote by capital P probability and so on. But here, I think that it is convenient. Is polynomial of then, of course, alpha must be equal to the sum from k equals 0 to some n ak hk of psi. And this representation of psi, this representation is closely related to representation p of x is equal to sum from k equals 0 to n ak hk of x. And such representation is unique. Yeah. So then one can do the following, take derivatives in the both sides, and finally one can continue this series and get that it is equal to sum from k equals 0 to n k ak h k minus 1 of x. So usually derivative of first course of analysis on this polynomial, which represent our function alpha, is written there. And one can see that now, of course, alpha has stochastic derivative because of this is not a series but finite sum. And you see that d alpha is equal to the sum from k equals 0 to n by our definition, k is k, hk minus 1 of hk minus 1 of psi, and is equal to p prime of psi. Okay. So you can see that if we have a representation of alpha as a polynomial of psi, then alpha must have stochastic derivative, and the stochastic derivative is simply the derivative of the represented function from psi. This gives us the idea. Maybe for this, at least for smooth functions, we must have the same. We must have this, and it occurs to be true. And let me check this. So let's take some other example. Let us take a good function. So consider alpha, which is represented by f of psi, and I will suppose that f is of C1 on our set of real numbers, and f and f prime are bounded. Let us check what happened now with the stochastic differentiability of alpha. To do this, we need to find coefficients ak, which are present here. F of psi now, this is our alpha, is equal to the sum from n equal to 0 to infinity, an hn of psi. So to continue consideration, we need this. And since we mentioned that Hn are orthogonal polynomials with respect to standard Gaussian distribution on R with the norm Hn equals square root of n factorial. Then it's easy to see that An is the integral, the 1 over n factorial. Here is integral with respect to R, f of x, Hnx e minus x squared dx and 1 over square root of 2 pi. Yeah. Now let us try to do the same for f prime and connect to this form. Of course, everybody understands that it can be easily done using integration by part. So let me do this. I will continue this formula, substituting instead of Hn its definition. So let me continue. It's equal to 1 over n factorial, 1 over square root of 2 pi, and here we have integral 1 over r f of x. Here we have minus 1 n. You remember formula for Hn in this formula, E and x square over 2 is present. So it will annihilate with this one. So we have d dx and here e minus x n minus x squared dx. Now I am changing, I'm integrating by parts, just taking one derivative from here to this. So I will have this one. I will have what? Since f is bounded and this function and its derivative is rapidly decreasing in the infinity, the terms from minus infinity and plus infinity will disappear. Then we have minus an integral with f prime and n minus 1. But we have here minus 1 in n power, so the answer will be 4. And factorial 1 square root of 2 pi, and here is integral r f prime of x, and here is minus n in n minus 1 d dx n minus 1 e minus x squared over 2 dx. Yeah. Now one can recognize here expression with the parent with Hermite polynomial of order h minus 1, and let us continue our formula. Let me do this just by arising. So I will get the following. I will get here h n minus 1, and here x e minus x squared, and then dx. So you see the following formula for an, and we relate it to the multiplication of f prime of x. So one can imagine that if we write the series for f prime of xi, suppose that it will be sum of n equals 0 to infinity. Bn here is hn of xi. Then one can see that hn, let me recall you that we have here this expression, sum n equals 0 to infinity an h and xi, that we have some relationship between them, and one can find this relationship easily. It can be checked from this representation of an, that we have exactly the formula which we are looking for. So we have the following relation. We have that Bn is exactly n plus 1, a n plus 1. So we understand that in this case, d alpha equals d of f of psi exists and is equal exactly f prime. Actually, here happened exactly situation which is familiar for us from the course of analysis about Fourier series. You remember that if we have a Fourier expansion of good function and want to have Fourier expansion of its derivative, we just change cosine and sine and multiply both of them on n. Here we have not cosine, sine, we have just Hermite polynomials, but we do exactly the same. We just make the multiplication and change by -1 the degree of polynomial. So such possibility to define derivative exists due to the good properties of Hermite polynomial, its recurrent formulas, and the properties that derivative of the Hermite polynomial of degree n is exactly n multiplied on the Hermite polynomial of degree n minus 1. Of course, exactly as in the theory of Fourier series, this definition covers not only such case of smooth function, smooth representative function here. And next lecture we will consider which new function here becomes to be stochastically differentiable. For today, that's all. Thank you for your attention. Maybe somebody have questions or comments, please. Okay.
Probably the question also where one can read this Darboux theorem.
Okay. It's good to look. For example, there is an old book of Achiezer. Maybe it's called problem of moments. You see, there are this is a very nice, very short book, but it is brilliant. There are a lot of good and interesting facts. arbitrary book related to the moment problem contains, of course, this result. I think that also you can take maybe a book of Bogachev, Gaussian measures also contain it.
Can you repeat the last item?
A book of Bogachev, Gaussian measures also contain. So it is interesting, but not hard statement. Okay.
Okay, thank you.
You're welcome. So for today's end, see you next week. Bye.